Today we're going to look at mean value theorem and Rolle's theorem. But first I want to take a look at this worksheet. If you don't have it, go print it off or watch it at least. Okay, so we want to take this function right here, and it's already graphed here. Okay, and draw the secant line connecting 3, okay, and f of 3, which is right here. And then 7 and f of 7. If you don't know what secant line means, that means a line that goes through the 2 points. Try to get as straight as possible. All right, so there's our secant line. Okay, there is a value, x equals c, between 3 and 7, at which the tangent line to the graph is parallel to the secant line drawn in part A. We want to draw the tangent line approximately. What is the value of c? So basically, where is this line, okay, parallel? And it looks like somewhere like right in here. If I draw, say, the tangent line right here, it's parallel. And where does that c value look like? It looks like it could be approximately, I'm saying 5.5. Okay, it might be like 5.4, and you can say that. Okay, we're just approximating. Okay, now we need to use our calculator to determine f of 3 and f of 7. So we would actually plug it in here. Okay, I've already done this, so I'm just going to tell you what it is. It's 2.3, and then when I plug 7 in, I get 4.3. Okay, then calculate the slope of the secant line. So think about slope. We put the difference in y's, so 4.3 minus 2.3 over, okay, and then it's 7 minus 3. Okay, so I get 2 over 4, which equals 1/2. All right, how do you determine the slope of a tangent line? Okay, well, slope of a tangent line, we would do the derivative. Okay, so let's go find the derivative. Okay, negative 0.3x squared plus 2.4x minus 3.6. And then determine the value of c for which the tangent line is parallel. So I said my value was 5.5. So what I'm going to do is I'm going to find the slope at 5.5. All right, and I get 0.525. Now I want you to look at these. Are these two close? Yeah, they're pretty close. So our estimate of 5.5 is not far off from that c value. All right, let's move on. Let f of x equal, okay, so we have this curve, and it's honestly the same curve as we had up here, but they've redrawn the line. There are two values of x equals c between x equals 1 and x equals 7, at which the tangent line are parallel to the corresponding secant. So this time we're looking at 1 and 7. Okay, if I draw a line, again, get as straight as possible. Okay, and I want to draw a line parallel. Well, parallel would be somewhere right in here, and somewhere, looks like right in here. Okay, approximately what are the values of c? We're going to say 2.1 and 5.8 or something. All right, and so if you got somewhere close to there, that's fine. Now let's use our calculator to solve for the values of c. Okay, so here, we want to do f of 7 minus f of 1. All right, and then 7 minus 1. 4.3 minus 2.5 over 6 equals 3/10. All right, so here we know the slope of this line is 3/10. To solve for the value of c, okay, we want to take our calculator and we want to take the derivative that we, in a sense, this is the same. We want to take this derivative up here and we want to say negative 0.3x squared plus 2.4x minus 3.6. And we want to know when it's equal to 3/10. All right, I'm going to say zoom 6. All right, so we have a quadratic. Here comes our quadratic. And we're basically finding the two places where they intersect, which is actually going to be our C values, okay, that have the same slope. Second trace, 5 for intersect, 1, 2, 3. Okay, and the 1 C value is approximately 2.268, and remember, round to 3 decimal places. Okay, second trace, 5 for intersect. All right, scroll right over. 1, 2, 3. Okay, and its C is approximately 5.732. Is it approximately what we said? Yeah, very close to it. All right. Now, new graph. Now let's look at this. All right, and this says to the 2/3. So 6 minus 2 times x minus 4 to the 2/3 as graph. So we got the graph right here. What is true about g of x at x equals 4? Okay, well, we talked about absolute max and min yesterday. So we know right here at x equals 4 is an absolute max on the interval. Okay, but what doesn't happen here? It's not differentiable. And why is it not differentiable? It's not differentiable because there's a sharp turn. It's not a quadratic. You got the sharp turn here. So there's actually a vertical tangent line instead. Now, is there a value of x equals c between x equals 1 and x equals 4 at which the slope of the tangent line equals the slope of the secant line? Okay, so let's look. X equals 1 would be here. X equals 4 would be here. Okay. All right. It appears that we can do a line that's parallel right here. And I'm going to add this at x equals 4. Okay, so let's approximate it. Now, the slope of the secant line would be f of 4 minus f of 1 over 4 minus 1. All right, I would find f of 4, which is 6, and then f of 1 is 1.8398 over 3, and this is approximately 1.3867. Well, you would want to do exactly what we did down here and set the derivative equal to the slope, which is this right here. Okay, well, the derivative of this would be negative 4/3 x minus 4 to the negative 1/3. Okay, and I would set this equal. And I would go back to my calculator and find where this intersects. All right, so here we go. We're going to do negative 4/3 times x minus 4 to the negative 1/3. And we want to know when this equals approximately 1.3867. All right, zoom 6. All right, so let's wait till it comes up, and then what we're going to do is we're going to find the intersection. And I notice, let's see, it looks like there's going to be one intersection point right here. So second trace, 5 for intersect. All right, and I get it at at x is approximately 3.111. Now, is there a value of x equals c between 1 and 5? Okay, so here would be 5 right here. All right, so here would be that secant line. Is there anything that we can make tangent right there? If you think about it, no, there's nothing we can really make tangent that equals the slope. And So here, no, because it's not differentiable between 1 and 5. We have this sharp turn here that's preventing me from finding a line that's tangent that would be parallel to the line from 1 to 5. All right. Now let's look at this. This is a piecewise function, and they've got it graphed here. Is the graph continuous from 3 to 6? Okay, and that's a closed interval. We say no. There is a jump and a hole. Is the graph differentiable on the interval from 3 to 6? Well, let's see. On the closed interval from 3 to 6. Well, 6 is right here. Okay, from 3 to 6, no. It's not differentiable because it's not continuous. No, not continuous. And for it to be differentiable, it has to be continuous. Okay, is there a value of x in the interval 3 to 6 for which h prime is c, the slope of the secant line connecting h of 3 to h of 6 right here? Is there one? Can we find a tangent line that is parallel to that? No, we cannot. So what we're discovering here is the mean value theorem. If you notice in each one of these graphs, if y equals f of x is continuous on the closed interval of a to b and is differentiable everywhere on the open interval, so it doesn't have to be at the endpoints, then there is at least, let's just say, one number, c, between a and b, at which f prime of c equals, and you saw us do this, f of b minus f of a over b minus a. All right, and let's go through this again. Basically, you have a secant line. As long as it's continuous and differentiable on the interval, then I can have a tangent line that has that same slope. Okay, and there's some c value where it is tangent. And in some cases, we saw one where it could be two places. All right, and just recall slope equals f prime of x. All right, so let's look at some of these problems here. We have f of x equals x squared on the closed interval 1 to 3. Then MVT states there's some number c, and we want to find that number c. Okay, so we want to find the c that satisfies MVT here. So MVT is f prime of c equals, we're going to do f of 3 minus f of 1 over 3 minus 1. Okay, f of 3, we'll think 3 squared is 9. F of 1 squared is 1. And we already know 3 minus 1 is 2. So this is 8 over 2, which is 4. Now, that's not our c value. This is what f prime of c is. This is the slope. Okay? So to find c, well, think about it. Slope is the derivative. Let's find f prime of x. All right, it's 2x. And we want to know when is f prime of x equal to the slope of 4. So I divide by 2, and I get x equals 2. Now, I want you to notice, is 2 on this interval? Yes, it is. So this satisfies, and so this is what c equals. So this satisfies MVT, the mean value theorem. We have a secant line that has this slope right here. Well, we can also have a tangent line that's going to have that same slope as long as this is continuous and differentiable, okay, on this interval. All right, let's do it again. Find the value or values of f of x, okay, on this such that satisfy MVT. So the first thing is, for MVT, we need to know, is it continuous and is it differentiable? Okay, and this is one of the things that I forgot right here. You need to write out to the side f of x is continuous on the closed interval from 1 to 3 and differentiable on the open interval from 1 to 3. Okay, so get in the habit of doing that, otherwise you will be taken off. All right, so right here. So is it continuous on the closed interval from -2 to 2? Yes, it's a cubic. Now, is it differentiable? Well, one thing you may want to look at is actually go find the derivative. This is 3x squared minus 12. Is there anything where this is undefined? No. So therefore, it's differentiable on this interval right here. So it's continuous and differentiable. So it applies with that. So now we can apply MVT. So f prime of c equals, we're going to do f of 2 minus f of -2, and then we do 2 minus -2. All right, f of 2, if I plug it in, and I'm plugging it into the original function, not the derivative, okay, f of 2 is -16. All right, f of -2 is positive 16. All right, and this makes 4 right here. So this equals -32 over 4, which is -8. Okay, so again, remember this is slope. This is not our c value. All right, so this is the slope of the secant line. Well, let's take f prime of x, which we just found a little bit ago, and we want to find this. What are the values of x, or we could plug c in there, that has that same slope. So here, I'm going to solve this quadratic. 3x squared equals, add the 12 over, and I get 4. Divide by 3, so x squared equals 4/3. And before I go off, I'm going to rewrite this right over here. I'm going to take the square root. Don't forget plus or minus. All right, so this makes x equals plus or minus 2 over the square root of 3. Now, do both of these actually work? And you got to ask yourself, are both of these in the interval of -2 to 2? And it is. All right, so these are our c values. We actually have 2 c values that work in this case. Moving right along. We want to find the value or values of f of x equals 1 over x on -2 to 2 that satisfy MVT. Well, what are the first 2 things that has to happen? It has to be continuous on the closed interval, and it's got to be differentiable on the open interval. Okay. Is this continuous? Is there anywhere on this that it's not defined? Think about it. Well, right here, what can x not be? It can't be 0. Is 0 on this interval? All right. 0 is on this interval, so we have a vertical asymptote at x equals 0. So therefore, it's not continuous. So MVT does not apply. And I don't need to put in that work towards it. All right, so make sure you check these first. All right, I got a quadratic here. Okay, we're looking on the interval from -3 to 4. Find values that satisfy MVT. And it could be values or value. We don't know if it's 1 or 2, and we'll have to verify that. Okay, so first off, is it continuous on the closed interval? Okay, well, yes, because a quadratic is always continuous. All right, is it differentiable? Okay, from the open interval. Okay, well, let's think about this. F prime of x is going to be 2x minus 1. Is there anything x can't be? No. So it is differentiable on that interval. All right, so now I can go ahead and apply it. F prime of c equals, we're going to do f of 4 minus f of -3 over 4 minus -3. Okay, so on this one, f of 4, if I plug it in, I get 0. And then here, if I plug in f of -3, I also get 0. So this is 7 down here, but it equals 0. So this time, it's when the slope equals 0. All right, so f prime of x. Okay, we set the derivative. Remember, that's the slope of the tangent line, equal to 0. So 2x equals 1, and we get x equals 1/2. All right, which would be our C value. And double check, is 1/2 on that interval? And it is. Okay, now let's think back to yesterday. Do you remember seeing this? F prime of x equals C. What did that mean that we had? All right, we had a local min or max. So all this kind of goes together. Now, not only is this the mean value theorem, there's an extension of the mean value theorem, and it's called the Rolle's theorem. It's got the same application. Let f be continuous on the closed interval and differentiable on the open interval. So this is the same thing as MVT. If f of a equals f of b, and we had that in the last case, then there is at least one number c in a to b such that f prime of c equals 0. All right, and here it just so happened f of 4 and f of -3 both equaled 0, but it could have been any number, but both of them are the same. So Rolle's actually applies in this place. All right, if you want a picture of Rolle's, it looks something like this. Okay, say we have a function right here. All right, we'll say this amount is A and this amount is B. All right, and they have the same value. So therefore, right here, the slope of their secant line, the slope is 0. All right, it is continuous. All right, it is differentiable. And look where C would lie. This would be C. C would lie right here, okay, which actually is at one of the turning points. All right, let's do another problem. We're going to satisfy MVT. Now, it might actually be a Rolle's, but we'll see. First things first, we have to decide, is it continuous on the closed interval? Okay, and it's a quadratic, so yes it is. Is it differentiable? And I went ahead and checked that off. Some of you are already going to check it off. If you want to find that derivative, you can. But that's continuous. I don't have anything that it's that I'm limited on. So therefore, f prime of c equals, all right, we're going to do f of 7 minus f of 1 all over 7 minus 1. All right. All right, now, here, what's f of 7? All right, when I plug in 7, let's see, it's 7 squared minus 8 times 7, all right, plus 15. We get 8, all right, and then when we do 1, let's see, that's 1 minus 8, which is -7. -7 plus 15 is also 8. All right, what do we notice about these? They're the same value. All right, so therefore, this equals 0. So therefore, f prime of x will be set equal to 0. And then we can find that c value or that x value where it equals 0. So we say 2x minus 8 equals 0. All right, 2x equals 8. Divide by 2, x equals 4. So that c value is 4. And is it on the interval? Yes. It is. All right. Now, why do we need MVT? In the coming days, we're going to talk about this more. We need it for increasing and decreasing functions. All right, and we can determine where it's increasing and decreasing and slopes and so forth. All right, and put this in your memory bank, but we're going to keep going over this in the coming days. Given an interval I and x1 and x2 in I, f of x is increasing over the interval if x1 is less than x2. That means f of x1 is less than f of x2. All right, if f of x is decreasing over the interval, if x1 is less than x2, but the y value, f of x1, is greater than f of x2. All right, so this happens. We can apply it to the first derivative. Okay, instead of just looking at the graph, and sometimes we don't have a picture of the graph, we can look at the first derivative. If the first derivative is greater than 0, then f of x is going to be increasing on that interval. And if f of prime, and I should have said prime of x, if f prime of x is less than 0, then f of x is decreasing on the interval. So, our question is, determine where each function is increasing and decreasing. Well, we don't actually have to find where and look at a graph on this. All right, I can find the derivative. All right, it's y prime equals 2x. And remember what we just said. When it's greater than 0, it's increasing. So here, x is greater than 0 is increasing. Okay, and this is the interval from 0 to infinity. Okay, and then here, when 2x is less than 0, it's decreasing. So x is less than 0 is decreasing on the interval of negative infinity to 0. And if I were to look at this graph, think about it. It's y equals x squared. Okay, isn't it decreasing from negative infinity to 0, and then from 0 to infinity it's increasing? And that's what we just stated, without actually having to look at the graph. All right, so let's look right here. A little bit harder. Now we kind of know the graph of this one, but we don't know the graph of this one. F prime of x equals 3x squared minus 4. All right, so 3x squared minus 4. Okay, it's increasing when it's greater than. Okay, so this is 3x squared greater than 4. So x squared is greater than 4/3, and we take the square root. Okay, but we got to be careful when we take the square root. It's x is greater than the square root of 4/3, or x is, don't forget about the negative case of it. And what happens is, with the negative case, I flip my sign. So this is when it's increasing. And instead of or, I should probably use and, because it's here and here is where it's increasing. Okay, so let's look at decreasing. 3x squared minus 4 is less than 0. So 3x squared is less than 4. If I divide by 3, I get x squared is less than 4/3. So here, when I take the square root, x is less than 4/3, or square root of 4/3. Okay, and remember with the negative, I flip my sign. This is where it's decreasing. And we're going to look further into that a little bit later as I go on. All right, so just look back over MVT. You will use it later on. It is something that could pop up again. And be careful. You always have to state if it's continuous on the closed interval and differentiable on the open interval.